Okay, so in this video, we are dealing with section 4.7 and continuing with electron configuration. And as you can see here, groups 1 and 2 belong to what is called as the S block. It's because of the way those electrons, the order in which they're filled, all right? The transition elements belong to the D block, and then groups 3A through 8A belong to the P block, and we'll see in a bit why this is so. So orbitals are shown as box diagrams. So there's two ways of showing them. One is where you write out the orbitals in the form of these boxes. That gives kind of clarity, and it gives a nice picture and good visual. This is the configuration, or configuration is another term for arrangement. All right, so this is the electron arrangement for carbon. So carbon has got a total of 6 electrons. It's element number 6. So the first two go into the 1s, then the next two in the 2s, and then the remaining two in the 2p. All right. Now, a lot of the times, an empty orbital like this is unstable. So sometimes an electron from a lower energy is promoted there because half-filled orbitals are more stable compared to an empty orbital that's lying vacant like that. So another way to depict the arrangement for carbon, or the electron configuration, is to write it this way: 1s2, 2s2, 2p2. All right. So if you count up the superscripts, 2 plus 2 plus 2, that's a total of 6. All right. So the superscripts represent the number of electrons. All right. And so this is an easy way to write down the electron arrangement for an element. So hydrogen can be depicted either with just the one box, or this way: 1s1, and helium as 1s2. And if you have 2 electrons, they have to be in opposite directions. Now, in addition to these box diagrams and the electron configuration this way, you can also have an abbreviated form of the electron configuration. So you can take the preceding noble gas, put square brackets around it. So when you do that, this indicates that you've accounted for the 2 electrons, and the remainder of the 1 electron goes into the next level, the 2s1. All right. So neon also can be represented that way, helium, and then the 2s2, 2p6. Sometimes I've seen students just taking the noble gas and putting a square bracket around it and denoting that to be the abbreviated form, and that would be incorrect. Right? It's always the preceding noble gas, and then you write that's accounted for a partial amount of the electrons, and then whatever is left over is then written out. So the guide to drawing these box diagrams, or these orbital diagrams, is write down the boxes that would represent the occupied orbitals, and if they're occupied, put a pair of electrons in them in opposite spins, and then any remaining orbitals will go into the last sub-level in separate orbitals. So nitrogen with 7 electrons. The first 2 go in here, the next 2 in here, and the remainder 3 go in single file. Remember Hund's rule, which says that if you have orbitals of the exact same energy, then the electrons cannot get paired up. They have to go in single file before the pairing up process starts. Okay. As well as those electrons will be facing in the same direction. They'll be of parallel spins. All right, so you have from sodium to argon, you can see that the third energy level is getting filled up. All right, n equals 3 is getting filled up by the time you get to argon. All right, so this is the S block, the groups 1 and 2. Then transition is the D, and the P block starting at group 3A to 8A, and then lanthanides and actinides. So S is 1A and 2A. 3A to 8A is the P block. D block is transition. And then the F block is the inner transition, or the lanthanides and actinides. All right, chlorine atomic number 17. How do you write its electron configuration? It's in group 7 and period 3. All right. So that's 1s2, then 2s2, that's 4 electrons, and then 3s2, that's 6 electrons. I'm sorry, 2s2 and then 2p6. So that would be a total of 10 electrons. So you have 7 left. So 3s2, and then the 5 electrons go into 3p5. Okay, so 1s2, 2s2, 2p6, 3s2, and then 3p5. Calcium, so potassium is 19, argon is 18, so 18 plus 1, 19, and then calcium is argon, and then 4s2. So the 4s sublevel is completed. Now the 3D starts filling up. So this is the order of filling. You first fill the lowest energy levels, and then the next higher, and the next higher, and so on. So the 1s, the 2s, the 2p, 3s, 3p, and now instead of going to 3D, there is a 4s. The reason for that is if you look at the number of orbitals for 3D, there's 5. So that means a total of 10 can fill up the 3D orbitals, all right? So 3D orbitals, electron is energy. So the 3D orbitals are going to have more energy compared to the 4s, which has got just one orbital, all right? That means only 2 electrons can go in. So even though it is of the next higher level, it's lower in energy compared to 3D. So after 3p, you see this happening. You see 4p, and it should have gone to 4d, but there is a 5s. So the next higher s is kind of wedged in between the p and the d. All right, now you come to 6s, and now here, before you get to even 5d, you have the 4f. All right, so some people like the step method, and this will be given to you in the exam, but others prefer this method to follow the arrows. All right, both methods are, I mean, whichever your preference is. All right, okay. So both methods effectively show you how the order of filling is. So you're simply following the arrowhead in this case, all right? So the first 2 in here, next 2 in here, the next 6 go in here, and followed by another 2 into the 3s, and then so you just follow the arrowhead. All right, and then you have the exceptions of chromium and copper. I explained about half-filled shells are much more stable than unfilled shells, all right? So empty shells. So orbitals. So chromium with 24 should have been 4s2 3d4, but it would have an empty orbital, and therefore one of the electrons gets promoted so that all the 5d orbitals have 1 electron in them, all right? So the d orbital is half filled, the s is half filled, and so this is more stable compared to 4s2 3d4. Okay, now same thing happens in copper. All right, it should have been 4s2 3d9, but that would have left one of the orbitals, like all the other d orbitals are fully filled, and then one orbital doesn't have a partner. So if you have a half-filled S and then a fully filled D, that is more stable than having a fully filled S and one single orbital in the D that is partially filled. All right, so those are the 2 exceptions. And then you have the continuing of the P block from gallium to krypton. And you can see here, once that 4s2 and the 3d is filled with the d with the transition metals, and you continue on, and then 3d10, and then 4p1, and so on. Okay. All right, so it says write the electron configuration of selenium with atomic number 34. Okay, so 2 in here, another 2 in here, that's 4, and then 6, so that's 10, 12, and another 6, so 18, and then another 2, so 20, and another 10 here, so 30, and then 4 in the 4p level. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. All right, we talked about chromium. It's more stable to have one electron in here and then promote one electron into the d level instead of having this fully filled and then one empty orbital in the d level. All right. Copper, again, if it was 4s2 3d9, this would not have a partner here, and therefore to promote one electron in here would make this fully filled, very stable, and this is half filled, and half filled electron orbitals are also stable. All right, use the periodic table to give the symbol and name for the element with the electron configuration of. All right, so 2, 4, 6, 10, 12, 18, 20, 27. So D means it's in a transition element, and 27, atomic number 27 is cobalt. Okay, write the electron arrangements for the following. Carbon, atomic number 6. So that's 1s2, 2s2, 2p2. Silicon, atomic number 14. And that's 1s2, 2s2, 2p6, 3s2. So that's 12, and 3p2. Okay. Atomic number 8, which would be oxygen, 1s2, 2s2, and that's 4, and 2p4. Okay. All right, so answer questions 4.49 through 4.66 on page 135. And that's the end of this video on section 4.6.